Sum of a geometric series. So what is the difference between a series and a sequence? A sequence is a list of number. Series is the sum of the entire list. So sequence, I will separate A1, A1, R1 by a comma. But for series, I will just add them all up. So there are two cases. We have a common ratio R when the absolute value R is less than 1. The sum is equals to capital S equals to the summation. I goes from 0 to infinity. A1 times Ri, and then that is equals to A1 divided by 1 minus the common ratio. Do you know that why the sum is not infinity? Do you know what I'm trying to say? We are adding up many numbers, right? So from the first term all the way to the nth term, n plus 1, n plus 2 terms. So when you are adding up a lot of numbers, so think about this. You have written many numbers on a piece of paper. You want to add them all up. Do we agree that the sum is getting bigger and bigger as you add more values to the sum, right? So we have many numbers. We add them all up. The sum is going to be a large value, but that is not necessarily the case. Look, when R is less than 1, so let's say 0.5, as we raise 0.5, the common ratio, to a very large exponent, what happened? When you take a 0.5, let's say you raise to 100 power, 1000 power, what happened? The product is nearly a 0, right? When you take a 0.5 raised to a very large value, the result is nearly a 0. But if you raise 5 to an infinity, the result is equals to infinity. So that's why there is a second case. When the absolute value of the common ratio is greater than or equal to 1, the sum is just equals to infinity. Because as you look all the way right to the summation, you will see that R is big. When you have a common ratio greater than or equal to 1, of course the absolute value raised to a very large power, the product is equals to infinity. So you are adding up a bunch of large value. That's why the sum is infinity. On the other hand, when the R absolute value is less than 1, when you raise that to a very large value or a large exponent, that is equals to 0. So that means as you move on to the right, you are just adding up a bunch of 0. So that's why the sum is not going to be infinity. Of course, we have an example for each case. So the first one, they match the color, all color coded, summation from 0 to infinity. So you are adding up infinitely many numbers, right? So in theory, the sum should be infinity, but this is not true in this geometric series. So you have 2 times 0.5 raised to the n, and then when n is equals to 0, you have a 2. When n is equals to 1, when n is equals to 2, when n is equals to 3. What happens when n is large, like this, 100 or 200, 500, or even 1000? What happened? So in this geometric series, the first term is equals to 2. So let's write this down. The first term is equals to 2. Actually, let's don't use a bold pen. A1 is equals to 2, and then the common ratio is equals to 0.5. And then the absolute value of common ratio is less than 1. And then therefore, the sum is equals to the first term divided by 1 minus the common ratio. 2 divided by 0.5 is equals to 4. And then what happened when n is large? So when n is very large, so these are nearly a 0. So 0.5 you raise to an infinity. So this one, when you raise that to 100, or you have a 0.5 raised to 2000, these are nearly a 0. So the value, although you are adding up many numbers, these numbers are nearly 0. So that means the sum is only determined by the first couple terms. From A1 probability from n equals to 0, probability to n equals to 10 or n equals to 15. So even though you are adding up many numbers, the sum is not necessarily infinity. So I'm going to say that the sum is determined by the first few numbers. How about the blue one? The blue one, the only difference is I changed the common ratio to a 3. So that is you have n equals to 1. So this is n equals to 0, n equals to 1, n equals to 2, n equals to 3, and then as you move on, you have n equals to 100. So what happened when you have 3 raised to 100, or 3 raised to 200, or even 3 raised to 20,000? These are all infinity, right? So I would just say an equal. These are infinity. So that means you are adding up a bunch of infinities. Of course, the sum is equals to infinity. The sum is equals to infinity because the absolute value of r, which is the absolute value of 3, is greater than or equal to 1. So you are adding up a bunch of infinity. So let's put it right here. So this, you are adding up. Let's use more space. Adding up when n is large. So when n is large, you are adding many infinities. So of course, the sum is equals to infinity. Okay, let's do a couple more exercise. So the next exercise that I would like to do is, I am going to give you a series. So this is a summation, n equals to 0 to infinity. So we are adding up infinitely many numbers, and then 2 times negative 2 over 3 raised to the nth power. So what happened when n is 0? When n is 0, we have a no fraction. And then when n is equals to 1, you have 2 times negative 2 over 3 raised to the first power. When n is equals to 2, you have 2 times negative 2 over 3 raised to the second power. And then when n is 3, negative 2 over 3 raised to the third power. And then you keep on going, right? So you will experience something like this. So when n is equals to 500, you have 2 and then negative 2 over 3. Let's make that look like a 3 raised to 500 power, and then you keep on moving, right? Now, do we agree that as n becomes very, very large, so negative 2 over 3 to the 500th power, or negative 2 over 3 to a very large power, so these are nearly either a plus or minus infinity. So even though you don't think about the plus or minus, just think about infinity, something that is extremely large, and then plus infinity and minus in. Okay, so I'm going to take this back. Look, negative 2 over 3 is less than 1, so r is equals to 2 over 3 in negative. The absolute value of r is equals to 2 over 3, that is less than 1. So that means the sum is not equals to infinity. And a good example, so this one I cannot put this as a fraction. You can think about that as something like this. So how about when you have 0.3 and then you raise to a large value, so these are nearly a 0, right? So let's say you have 0.75, you raise to a very large value, that is nearly a 0. I don't really care positive or negative. So every time you look at a geometric series, look at the common ratio. So this common ratio is negative 2 over 3, which is negative 0 point something. When you take the absolute value of that, that is less than 1. So that means when you take these numbers, something like 0.2, 0.5, 0.75, you raise to a very large value, the result is nearly a 0. So this result is nearly a 0. What is that means? That means, and when n becomes big, so when n is large, you are adding up a bunch of zeros. So you are adding up many zeros. So which means the sum is determined by the first few terms. So the sum is determined by the first few terms. Probably when n equals to 0 to n equals to 15, because when n is large, you take negative 2 to the raised to a large exponent, it's just a 0. So we do not need to count those at all. Alright, so the sum is determined by the few terms. Then what is the sum then? Then the sum is equals to, a1 divided by 1 minus r. The first term is 2, and then you have 1 divided by the common ratio. So that is equals to 2. 1 plus 2 over 3, that is 5 over 3. You flip the 5 to the top. 2 times 5 is 6. 6 over 5. So the sum is actually not that large, even though you are adding up infinitely many numbers. Okay, let's talk about the next problem. The next problem, let's pick a different color. Let's pick a yellow. So this one is summation. N equals to 0 to infinity. You have 0.8 raised to the nth power. Okay, so we don't have a number in front of that. You can treat the number in front of the parenthesis equals to 1. So what happens when n equals to 0? You have a 1. When n is equals to 1, you have a 0.8 to the first, right? When n is equals to 2, 0.8 to the second. When n is equals to 3. When n is equals to 4. When n is equals to 5, 0.8 to the fifth, and then you keep on going. Eventually, you will see something like this, raised to the 500 power, and then you keep on moving, right? So 0.8 raised to 500, these terms are nearly 0. 0.8, 0.81, as long as that number is between 0 and 1 and 0 and -1, you raise that to a very large value. Just try this on your calculator. You will just get a bunch of zeros, right? So the common ratio is equals to 0.8, and then the absolute value of 0.8, that is less than 1. So the sum is equals to A1 divided by 1 minus R, which is 1 divided by 1 minus 0.8. 1 divided by 0.2 is equals to 5. 0.2 is 1/5, so the sum is equals to 5. So even though you are adding up infinitely many terms, the sum is only determined by the first few terms. Let's see the last question. The last question is not so obvious compared to the rest. You have 9 plus 6, and then plus a 4, and then plus 8 over 3. So this time I don't have the series in a summation symbol. Then what do? This is I will treat this as the first term. The first term is equals to 9, and then you are talking about geometric, right? If you don't give me the common ratio, I will just go ahead and look for it. And then the common ratio is the next term divided by the previous term. This is a 2 over 3, and I will make sure this is true for every single pair. And then 4 divided by 6 and 8 over 3 divided by 4, they are all 2 over 3. So I know that the common ratio is 2 over 3, and then the absolute value of that is less than 1. So that means the sum is not equals to infinity. Okay, so what is the sum then? The sum is equals to the first term, and then 1 minus the common ratio. The first term is 9, 1 minus the common ratio, 2 over 3, so which is 9 over 1/3. Flip the 3 up, so you have a 27. And then do you see that the numbers are getting smaller and smaller from 9 to 6 to 4 to 8 over 3. Eventually, as you look all the way to the right, those numbers are so small, they are so close to 0. So that means the sum is really determined by the first few terms, which is 27. Alright, so this is the end of this video, and this is also the end of my introduction to the sum of an infinite geometric series. If you think this video is helpful, give this video a thumbs up. If this is something that you want to teach, my teaching fits your learning, click the subscribe button for me. I'm sure it is worthwhile coming back to visit more math content. As always, I will meet you all in the next video. Take care.